So the first electron will go in, the second electron is going to go in there. Can I put the third electron there? No, because an orbital can only handle 2 electrons. So this is now filled. So what's next? What's the next best place to put them? The 2s. So I'm going to put the next one right here. Notice that this is a 2p, but 2s is lower in energy. So I'm going to put the next one there, and then I'm going to put the next one where? The 2s. And where am I going to put the next one? The 2s is filled now. Okay, the 2s only has 1 orbital, and that orbital is completely filled. So now, after 2s fills, now on the 2p. Now watch though. The 2p, I can put it in any one of these orbitals. They're all equal in energy. I'm going to, by convention, put it into the m sub l value equaling -1. So the first one's going to go right here. Where should I put the next one? Well, those of you who live at home with siblings, maybe you know this firsthand. Unfortunately, maybe you don't. But I can tell you this, as much as my sisters loved each other, they were much better when they had their own room. Okay? There's a certain amount of friction that develops. Okay? If you have electrons, sure, all those orbitals in the 2p are equal in energy, but you can minimize the repulsion that naturally exists between electrons if you put them in their own room first. That's the whole reason behind Hund's rule. Page 15, Hund's rule states that degenerate orbitals will each receive a single electron before pairing begins. Okay, by pairing, we mean a pair of electrons means electrons. Anytime you hear the expression paired electrons, we mean electrons belonging to the same orbital. So that means that the first one, the next one's going to go here, and then and only then will I begin pairing up before I move on. And finally, the Pauli exclusion principle basically states that no 2 electrons in the same atom in the ground state will have the same 4 set of quantum numbers. So that means that they could be in the same energy level, the same sublevel, the same orbital, but they'll have opposite what? Spins. So that 4th quantum number will be different. By the way, turn back to page 14. It's time to redefine ground state. So from here on out, when I ask you for the definition of ground state, this is what I'm going to ask you for. Ground state is now defined as this. Ground state is when all the electrons of an atom, are in the lowest energy orbitals available. Okay? Remember before, some of the electrons on lowest energy level. No, not anymore. Now ground state is when the electrons are in the lowest energy orbitals available and all paired electrons have opposite spins. Again, by paired electrons, we mean electrons belonging to the same orbital. So ground state again, when all the electrons of an atom are in the lowest energy orbitals available and all paired electrons have opposite spins. Guys, this model of the atom is just a wonder to behold. It's complex and as weird as it looks. It seems to be we're standing up to the test of time, at least so far. Again, I'm not going to bet my life on the darn thing. I've seen us get, turned around thinking we had an answer for a good number of years, only to find out was the case. But this still explained line spectra. Remember how Bohr explained line spectra? Said line spectra was the result of the electron absorbing or emitting specific photons to undergo electron transitions. Each photon has associated with a particular frequency, which corresponds to a line-in-line spectrum. Okay, that explanation is exactly the same explanation as before, with one difference. In Bohr's model, an electron transition is when the electron would jump from one energy level to another. Now, Julia, an electron transition is when it jumps from what? Orbital. From one orbital to another energy orbital. So, in order to jump from, let's say, the 2p sub z up to the 4s, it's going to require a certain amount of energy. That's going to have a photon. That's going to line up with a particular frequency, which corresponds to a line-in-line spectrum. So we explained line spectrum the same way as we did before. It's still the result of the electron absorbing and emitting photons undergo electron transitions, but now electron transition refers to the electron jumping from one energy orbital to another energy orbital. Questions? Okay, at the top of page 14 are a couple of terms I just want to make sure that you're familiar with. Diamagnetism and paramagnetism. This will become more important as we go along into bonding. Diamagnetism and paramagnetism, guys, are not what you think of when you think of magnetism. When you think of magnetism, you're thinking of what is known as ferromagnetism. Ferromagnetism, ferro, F-E-R-R-O, what suggests what element? There's actually only 3 elements, common elements, that are ferromagnetic, okay, or ones that you think of being able to pick up. Iron, cobalt, and nickel. Okay, a magnet will affect them. Aluminum, zinc, yeah, magnets don't affect them. Diamagnetism, paramagnetism is a different form of magnetism, it's much weaker. You'll look at it, it says diamagnetism is the property of weak repulsion to a magnetic field arising from the absence of unpaired electrons, while paramagnetism is the property of weak attraction to a magnetic field arising from the presence of unpaired electrons. You need to know which is which. You've got to keep these definitions straight. So that means you have to come up with some sort of mnemonic device that will sort of help you. Now, you might be wondering to yourself, when they say under diamagnetism it's the absence of unpaired electrons, what that really means is that all the electrons are what? No. If there's an absence of unpaired electrons, that would suggest that all the electrons are paired. Okay? So why did they just say that? Well, it has to do with the way this was discovered and how they define it. Let me explain what that means. If it were paramagnetic, okay, I could have a test tube full of that element, and if I tied it to a piece of string and I brought it into the place and brought it in close toward where, let's say I brought the string tied to the test tube into the place of a magnetic field, if the test tube moved toward the magnetic field, that would be a weak attraction, that would be paramagnetic. If I saw it sort of moving away from the magnetic field, that would be a weak repulsion, that's diamagnetic. You guys with me? I personally, to figure out a way to remember these definitions, the way I did it. This works for me. If it didn't work, you can come up with your own. I think of it this way. I think of the fact that diamagnetism. Die. I am repulsed by dying. And die means 2, so everything's in 2s. So that's how I remember the diamagnetism is the one that deals with repulsion, and all the electrons are paired up. Now that works for me. If it doesn't work for you, you're going to have to come up with your own way of remembering. But you got to keep the 2 straight. Questions? This is so awesome. We covered so much today. Take a look at page 13. Okay, up here, guys. How many electrons can fit into the first energy level, maximum? 2. How many can fit into the second? 8, because I can get 2 into this sublevel and then another 6 into the S, right? 8. How many will fit into the third? 18. How many will fit into the ninth?
32. Oh, 9.
Ninth energy level.
I take 1.
Well, that means 9 sublevels with their orbitals. Well, have you seen how there's patterns here, guys? Well, there's mathematical relationships as well, so you don't have to actually physically go through the process. So at the bottom of page 13, you'll notice a nice little formula you might want to remember, which is the theoretical maximum number of electrons that can fit into an energy level is equal to 2n squared. That's worth knowing. That's worth remembering. 2n squared, so if it's the 9th energy level, that would be 2 times 9 times 9. Okay, so 81 times 2, in other words. You guys understand? Okay. What's the maximum number of orbitals that will fit into the 9th energy level? 81. How did she know that? Well, because she knows, if you know how many electrons, do I need that many rooms? No, because I can put 2 electrons in a room, right? So all I need is half that number. In other words, if 2n squared gives you the electrons in energy level, n squared gives you the number of orbitals in the energy level, right? How many sublevels are in the 9th energy level? How many sublevels? 9, right? And now you see the problem. You've got to be careful about what I'm asking. Am I asking about energy levels? Am I asking about sublevels? Am I saying about orbitals? Am I talking about electrons? Reading comprehension becomes critical. Thank God this doesn't happen often. It used to happen, but I warn people, so it doesn't happen as much anymore. But every 3 or 4 years, sometimes 5 if I'm lucky, it'll happen, and you'll see it. The person gets their test back, and And yeah, the tears and the cheeks are pink and they're looking at it. They knew this stuff so well and they totally screw this part of the test and it's all reading comprehension. You've got to pay attention to your reading. So you've got to be careful. What am I asking about? For instance, give you an example. What is the maximum number of electrons that can fit into a 4D sublevel? The maximum number of electrons that can fit into a 4D sublevel. The maximum number of electrons that can fit into a 4D sublevel. A 4D sublevel has how many rooms? 5. And how many electrons can fit into each? 2. So how many is that total? 10. What's the maximum number of electrons that can fit into a 6D sublevel? It's still 10. It doesn't matter what D sublevel we're talking about. You guys understand? Want me to go again? What's the maximum number of orbitals that can fit into a 5F sublevel? Maximum number of orbitals that can fit into a 5F sublevel.
7.
Maximum number of orbitals that can fit into a 5F sublevel. 7. You understand, Michael? Okay. You guys starting to get the hang of this? Maximum number of electrons that can fit into a 6p orbital. The maximum number of electrons that will fit into a 6p orbital. No. The maximum number of electrons that will fit into a 6p orbital. 2. Because it's an orbital, not a sublevel. Oh, yeah. Now you're starting to see it. Okay, you with me? All right. Maximum number of orbitals in a 3F sublevel. Maximum number of orbitals in a 3F sublevel. No. 3F doesn't exist. There is no 3F. There's only a 3D. The third energy level only has SP and D. It doesn't have that. Right? Well, that's a trick question. I asked you how many wings a pigs have. How easy of a question is it? 0. It doesn't have any wings. I mean, that's not a trick question, guys. That's an easy question. Usually hope I ask you stuff like that. Questions at all? All right, you got the wherewithal. You know what to do. Worksheet 2, due Monday.
Hey, that rhymes. Test Tuesday.
Okay, I think I want to add to that worksheet. Get the worksheet out real quick. Oh no, I already did it. Never mind. We're good. We're good. Oh, I know. We want to expedite things. So here's the key. Wait. If anyone's going to see Bree or anyone else who's absent, you can grab a key for them. Want to grab one, Joe, for Bree and Mary?
Yes.
You see Bree?
I have her next period.
She's gone.
Oh, never mind.
I'm going to give you one for Bree and Mary. If we leave it to Mary, you give it to her. All right, there's the key for that one. Let me do this too. Just stay where you are. Let me give you the key for the third one too while we're at it. As soon as you get this, you can go. Beautiful. Have a good weekend.
Yeah, except I have classes to do. I have ceramics and she doesn't let us do anything except ceramics.
Yeah. Well, yeah, just bring them up here, guys. Thank you. Thank you. Joe, don't forget your phone. Joe, your phone? Okay. What a great class today.
Can I get this form signed? I forgot.
How come you didn't bring it up when I was calling for everybody to turn them in?
I couldn't find it.
You couldn't find it, huh?